Well, there's an alternative representation of these same equations, which hopefully will be easier. Now, one complication here is that this matrix that we wrote over here is not symmetrical, not anti-symmetrical, etc. That is one thing that is not so nice. So let us just write it in a more symmetrical way. We can also write the same equation above. You see, this is our equation. Let's also check the dimensions A and B, if you remember their expressions. Well, this is nothing but our A. This is nothing but our B. A and B have the same dimension, right? So I would rather construct a matrix that contains objects of the same dimension. A and B squared, they don't have the same dimension. So let's write it in this form. This is equal to A minus B, B 0, no, B, Bn minus 2, Bn minus 2, B, Bn minus 3. Let's see, the first line is again my equation. Bn minus 1 is equal to A times Bn minus 2 minus B squared Bn minus 3. That's the equation I want. The second line is just B times Bn minus 2 is equal to B times Bn minus 2. But now the matrix is antisymmetrical. That will be easier to deal with. And we can even write it in this form. No, let's just leave it in that form. Now what we want to do is A minus B, B 0. Now an antisymmetric matrix, we can write it as we should be able to write it as a antisymmetric term times a symmetric one. The symmetric one is will be easier to diagonalize. We will be able to use an orthogonal transformation to diagonalize the symmetric part, right? Let's try to write this in this form. No. Okay, we will diagonalize that. And when we diagonalize it, it will be some matrix, M1, lambda 1, lambda 2, 0, 0, some matrix, the same matrix, inverse. This will be how we can diagonalize a matrix, an arbitrary matrix. Well, eventually we will do that. You see, our matrix A actually contains an I. Remember, you see, we have this part, the action, but the action will be multiplied by I over H bar. And what we know is we have, let's say over here, what we had proven, if we have a matrix whose exponent is minus xi, xj, aij, minus, then the integral is the determinant of A. And our condition will be the eigenvalues of A should have real parts that are positive. That is our condition. Now here, the aij's, this is our action, but the action is multiplied by I over H bar. So in the definition of aij, we should have minus I over H bar. So that the exponent will be e to the power minus xi, xj, aij. So here, our matrix A, let's just call this, this is our matrix A, where A will be minus I over H bar, 2m over epsilon squared minus m omega squared, and B is equal to minus I over H bar minus M over epsilon squared. Epsilon. This is our A and B. In fact, we can even do one more step. A, no, we can leave it like that. A, B actually contains that I that you are looking for. But we shouldn't be needing that. Now, anyway, let's stick with this one. Lambda 1 over lambda 2. Now, when we take this n minus third power, this will be m to the power minus 1, lambda 1 to the n minus 1, n minus 3, lambda 2 to the n minus 3. And remember, eventually we are taking the limit n goes to 0. If lambda 1 is larger than lambda 2, we have these two eigenvalues. One of them will be larger than the other one. Let's call the larger one to be lambda 1. Then lambda 1 to the power n minus, or let's see, lambda 2 over lambda 1 to the power n minus 3, this just goes to 0. So basically we can just ignore the lambda 2. Now of course we still need to calculate this matrix M. Well, let's do that. A minus lambda minus B. This is equal to lambda squared minus A lambda plus B squared. This should be equal to 0. So we have these two eigenvalues. This is A plus or minus square root of A squared minus B squared over 2 minus 4B squared. And A minus B, B0. Let's say the eigenvalue is xy. This is equal to ax minus by, bx. This should be equal to lambda plus minus x and y. So bx should be equal to y times lambda plus minus. So we can just choose our eigenvalues to be, if y is b, x is lambda plus or minus. So these are our eigenvectors. The matrix M, we can just write it as lambda plus b, lambda minus b. M inverse, determinant of M will be b times lambda plus minus lambda minus, which will be b times square root of a squared minus 4ab. So M inverse will be 1 over b times square root of a squared minus 4ab. No, I'm sorry, a squared minus 4b. So it should be b lambda plus minus lambda minus minus b minus lambda minus. So is this the, yes, this is the inverse. So let's see, bn minus 1. This is equal to, well, we are basically using this one. M inverse, now bn minus 1, b times bn minus 2, This is equal to 1 over b square root of a squared minus 4b squared, b minus lambda minus b lambda plus lambda minus to the n minus 3, lambda plus lambda minus b. Well, we already had calculated b2 and b1, a squared minus b squared and a. No, let's see. b1 is a. No, b2 is a squared minus b squared. And b times b1 is just ab. Okay, so we actually have the b's. And the next, put it here, multiply them. And that would give you bn minus 1. And you can just keep the lambda plus, because the lambda minus will be negligible compared to the contribution of the lambda plus. And in the limit as n goes to infinity, it will be 0. And we also know what a and b are. So basically, we are done calculating this part. Now, only this part, because you see this will be just an overall coefficient, we still need to calculate the classical action for the harmonic oscillator. This will be another long calculation, which, well, actually I am bored. Probably you are also bored just watching these calculations. So if you are interested, you can just do it at home. So now, okay, so we have the, okay, now why did we calculate the harmonic oscillator? Actually, the reason is right over here. Whatever your problem is, eventually it reduces to the harmonic oscillator plus corrections. So those higher order terms which we show as the ... they are the higher order corrections that will appear. So on the base we have the harmonic oscillator, and then there are the corrections, which we can, most of the time we can treat them as perturbations, especially if we are close to the ground state or at a low enough temperature. Now let's see how we will be doing those perturbations. Now let's do one more step in our integral. We had calculated this one. To this one, let me add one more term. I'm just adding one more term. The reason will be, I mean, if, for example, if I want to calculate dx1 dxn times, let's say, xk, if I want to calculate this term, let's just call this our z as a function of j. This term will be nothing but this is equal to derivative of z with respect to jk, evaluated at j is equal to 0. So once I know z of j as a function of j, then I can calculate whatever function is multiplying that exponent just by taking derivatives. Now this j is most of the time called the source. Now what is this term, by the way? This term is actually nothing but, if you remember, we were evaluating the integral from x, the evolution of my particle from x prime to x, e to power minus beta, e to power I over h bar, no, minus I over h bar, ht. This was the total thing. Now we will see our motivation later on, but I can divide this time t into smaller parts, let's say t1. Then I can have an x over here, and then I can have minus I over h bar h of t2. And then t1 plus t2 will be equal to my total time t in my path integral. And t1 is equal to epsilon times k. So I just evolve my state by t1 first, and then insert an x, and then evolve my state by t2. The total evolution time, we can say, we define it to be t. And since I'm inserting the x after I evolve my state by t1, and t1 I just divide it into k intervals. After that I have my x, so that's why xk appears over there on the top. So if I want to calculate this matrix element, for example, which is equal to this one, of course with the aij suitably identified, but then that one I can just calculate using this one, using the first line. Just taking with derivative with respect to j, and after taking the derivative, just setting j is equal to 0. Well, that one will be easy to evaluate. You see, if there were no matrices, it was just one-dimensional integral. What do we do in the one-dimensional integral? Minus x squared alpha minus jx. We just write this as dx e to power minus alpha times x squared plus j over alpha x plus j squared over 4 alpha squared minus j squared over 4 alpha squared. And then the result is dx e to power minus alpha x plus j over 2 alpha squared times e to power j squared over 4 alpha. And the first one is just pi over alpha square root e to power j squared over 4 alpha. And if now we have this expression, not a single variable, but many variables. This will be, let me just divide by square root of pi to the power n, just to get rid of that square root of pi on the right hand side. This will be equal to 1 over square root of determinant of a times e to the power 1 over 4 j transpose a inverse j. Now, we will basically do the same thing. You see, here we have x transpose ax plus xj. Let's see what we had done over here. We had replaced x plus, now we have replaced x by x minus j over 2 alpha. I'll just do the same thing over here. Replace x by x minus a inverse, no, j times a inverse. So if you just put it over there, x transpose minus j inverse, no, hold on, let's just do it this way. We will be changing variables. Let's just say x is equal to x plus y. Now we will determine what y is. What y should be, so that linear term, no, x is equal to y plus delta. We will determine what delta is. If we can determine that, we will determine delta by the requirement that the linear terms in y, it disappears. So if you just put it over here, this is equal to y transpose plus delta transpose A y plus delta plus y plus delta j y transpose A y transpose y plus delta transpose A y plus y transpose A delta plus delta transpose A delta and plus y times j plus delta times j. So what we want is delta transpose AY. Sorry, this is X transpose J. So this is Y transpose delta transpose. X transpose J is equal to J transpose X. Delta transpose AY plus Y transpose A delta plus Y transpose J. This should be equal to 0. Y transpose J is equal to 0. Or A delta plus 1 over 2 J should be equal to 0. Or to see it more clearly, the first line is delta transpose AY plus Y transpose A delta plus 1 over 2 Y transpose J plus 1 over 2 J transpose Y. This is equal to delta transpose A plus 1 over 2 J transpose Y plus Y transpose A delta plus 1 over 2 J. This should be equal to 0. If this one and this one, they are just the transposes of each other. Remember, A is symmetric. So if one is 0, the other one is also 0. So delta should be equal to 1 over 2 A inverse J. If this is the case, then let's see, this one cancels this one and cancels this one. That was the condition we had chosen. So X transpose AX plus X transpose J, this is equal to Y transpose AY. Now what remains is a delta transpose. Well, delta transpose is 1 over 2 J transpose A inverse. This is delta transpose A delta A. Now delta is another 1 over 2 A inverse J. And then we have delta J plus. Now, did we do a mistake over here? Delta transpose J, yes. Delta transpose is J transpose A inverse J with a 1 over 2. So here, let's see, do we have any other mistakes? So these are linear terms, they cancel. We have delta transpose J, delta transpose A delta. Yes?
John, how did you write Y transpose J as 1 over half, 1 over 2 Y transpose J plus 1 over 2 J transpose?
Which one?
The second one.
This one?
The one above.
This one? Because Y transpose J is equal to J transpose Y. Both of them are equal to Ji, Yi.
Is it product symmetric?
Well, both are column matrices Y and J. And now delta transpose AY is Y transpose A delta. True. True. Because A is symmetric. We could have done that too. So finally, e to the power minus x transpose A times x minus x transpose J. This is equal to e to the power minus Y transpose AY. And yes, I know where we made the mistake. Delta is minus this one. So this factor over here is minus times e to the power 1 over 4 J transpose A inverse J. And this, the only y-dependent term is over here. This is just a shift of variables. It doesn't change our measure. The integral over x1, xn is equal to the integral over y1, yn. With this, since they are both go from minus infinity to infinity, y's also go from minus infinity to infinity. And so this integral of e to the power minus x transpose A x minus x transpose J, this is equal to dy1 dyn e to the power minus y transpose AY e to the power 1 over 4 J transpose A inverse J. And we already know what this J transpose A inverse J term is independent of Y. We already know what the first term, the integral of the Y's are. So this is equal to 1 over square root of determinant of A times e to the power 1 over 4 J transpose A inverse J. Now, no minus. Now, what is this A inverse? Now, before we had the n minus 1 matrices, we were supposed to calculate their determinants, and now we need to calculate their inverses. Well, in the matrix operator formal expression is easier. Remember what the definition of A inverse. You have Aij, multiply it with A inverse Ji, Jk, this should be equal to Kronecker delta Ik. In the harmonic oscillator example, this is nothing but minus d squared by dt squared m minus m omega squared g of t and t prime. This will be equal to Dirac delta t minus t prime. It's nothing but our Green's function. So in principle, you can obtain your Green's function and just use it over here. And once you know your A inverse, let's say, remember this matrix element that we were looking for. This was equal to, well, we have the e to the power I over h bar is classical without the j. This is equal to dxi x of t1 e to the power I over h bar s. Now to this one we also added plus I over h bar x of t j of t dt. And this one we wrote as e to the power I over h bar is classical. Now this classical is the classical action in the absence of j. dxi. Now this one we just wrote as the functional derivative with respect to j at the time t1 of e to the power I over h bar. Let's say S tilde, that is whatever remains, plus x transpose jt dt. Now, here we don't have this jt part. So we just add it, take derivative, and then set j is equal to 0. Now this is equal to S classical t1 e to the power dt1 dt2 j of t1 j of t1 t2 j of t2 1 over 4. This is nothing but t times A inverse times t. A inverse is what we call the G. It's just J times A inverse times J. A inverse, we just named it G. And set at J is equal to 0. Which is well, there is one mistake I did. Let me correct it. I'm actually calculating this one. Because you see, when we just separate the x classical to, this is the x appearing over here is deviation from the x classical. So this matrix element is 0. Now that's kind of what we expect, because fluctuations to one side of x classical will be equal to the fluctuation to the other side of x classical. Now the easier one would be this one. X classical is equal to 0. It doesn't move at all because it starts from 0, ends at 0. It doesn't move. This is trivially 0. Now let's see. Let me just write it this way, T1. Now these are not time-dependent operators. It's just I'm first evolving my state by T2, then inserting my x, then letting it evolve by some other time, and then inserting my x, etc. This will be equal to del squared by del j T1, del squared j T2 of my z of j This classical for this path will also be 0. Well, this is nothing but g of t1, t2. This one will be kind of fun. Again, I have all the Hamiltonians in between. By the way, this is kind of a time ordering that I'm actually doing. If you see, I mean, you see, I have my state, I evolve by t1, then I insert an x at that time t1. I evolve it by some more time, then I insert another x at that time. Well, that's kind of, I'm time ordering my x operators. Now we can actually take the derivatives. You need to take 4 times derivatives and eventually set j is equal to 0. So this will be equal to g of t1, t2, g of t3, t4, plus g of t1, t3, g of t2, t4, plus g of t1, t4, g of t2, t3. How many of you are taking particle physics? You are taking? You are, no. Anyway, at least for you, it will, these will be familiar as path integrals. So you are kind of, you can just show these as, I have these 4 times, t1, t2, t3, t4. Now t1 and t2 are connected, t3 and t4 are connected. Then I have t1, t2, t3, t4. T1 and T3 are connected, T2 and T4 are connected. And then I have, again, T1, T2, T3, T4. T1 and T4 are connected, T2 and T3 are connected. This is just an alternative way of deriving the Feynman rules. Now, why do we need these to start with? Let's see, eventually we want to calculate this one. This we had already seen that this is equal to dx e to power I over h bar dt L0 minus V. L0 is the Lagrangian corresponding to the Hamiltonian H0. Now V will be a function of x. Of course, here it will be x of t. Now this, let's say this will be equal to dx e to power I over h bar dt L0 minus V of x of t. Let's add j of t, x of t. And j, we have to set j is equal to 0. But if we have this j, any x, x of t, we can replace it by the functional derivative with respect to j of t. Well, we have the h bar over I. So this will be equal to dx e to power minus I over h bar dt v h bar over I, the functional derivative with respect to j of t, e to the power I over h bar, let me just write s0 plus jx. But now, this is just an operator which doesn't depend on x. I can just take it out. Dx e to power I over h bar is 0 plus j of x. But this is what we call z, let's say, of 0, j. Of course, once we evaluate this by taking the derivatives, we have to set the source to 0. So basically now our main object will be this one, the partition function with the source. Now, once we have them, we can basically evaluate everything. Now, of course, this is a bold claim, meaning that we have that exponent over there, which contains the function of an operator. So what you need to do is you just expand that exponential, and also v, take sufficiently number of derivatives, and if v is small in some sense, then you can just cut that expansion at a given order, and so you have an approximate expression for z0. And anything beyond the z0, you can just choose. That's what we always do. We choose the harmonic oscillator part as our z0, and any corrections as our v. The harmonic oscillator we can evaluate. We can also evaluate it with the source, so we can just consider this expansion. Okay, so on Tuesday, we will just go over your exam, which you will pick up tomorrow. And on Friday, we will do an example of this one, how to calculate, for example, the energy corrections to the harmonic oscillator if we add some unharmonic terms. Then probably it will make more sense. Now, any questions? Well, I mean, this is a vast subject. I'm mainly telling you these subjects basically so you have an idea that, I mean, at the end of this lecture, if you say that, oh, there was also something called path integral, then that would be enough for me. Okay. Okay, so you will pick up your midterms tomorrow and turn them in on Tuesday morning.